Hello. In this video, we're going to talk about directional derivatives and gradients for functions with three variables. So all the videos I've done so far in this series have only been for two variable functions. So if we have a differentiable function of three variables and a corresponding unit vector, so u is u sub 1 I plus u sub 2 j plus u sub 3 k. So we're dealing with this curve in space. Then the gradient of f is the partial of f with respect to x, I, plus the partial of f with respect to y, j, plus the partial of f with respect to z, k. So we're just adding, for this third term, z or my k, we're just adding that third partial derivative. Similarly, that directional derivative, if we know the gradient, so the derivative in the direction of u for f is the gradient of f dotted with u, which gives me the partial of f with respect to x, u sub 1. Plus the partial of f with respect to y times u sub 2 plus the partial of f with respect to z times u sub 3. And this directional derivative, which we previously wrote as delta f dotted with u, again, that's the same as the magnitude of f times the magnitude of u times cosine theta. And since u is 1, we can remove that and we just say the magnitude or the length of my gradient times cosine theta. And all of the other properties for functions of two variables extend to three variables. At any given point, the function increases most rapidly in the direction of positive gradient f and decreases most rapidly in that opposite direction, negative gradient f. And any direction which is perpendicular to gradient f, that means the derivative is 0. And that is, think about the derivative equal to 0 in Calc 1, slope of the tangent line. So if you recall from the video before this, where we talked about writing the equation of a line tangent to a level curve, we were dealing with that gradient equal to 0. So now let's look at an example. In this example, we're going to find the derivative of the three variable function f of x, y, z, which is x cubed minus x times y squared minus z at point P, P naught, 1, 1, 0, in the direction of the vector v, which is 2i minus 3j plus 6k. All right, so the first thing we're going to do is find our directional derivative. And if we want to find the directional derivative, we need the direction, which means we need the direction of v. So the first thing we're doing here for part A is the direction of v, which is going to be our unit vector, which is found by taking v and dividing it by its magnitude. So the magnitude of this, 2 squared plus negative 3 squared plus 6 squared, that's going to be 49, so root 49. So u is 2i minus 3j plus 6k divided by root 49, which is 7. So we can say that u is 2/7 I minus 3/7 j plus 6/7 k. So I have my unit vector. Now I need my gradient of f, which includes the partial of f with respect to x, y, and z. So second, we need our gradient. And the gradient we need partial of f with respect to x, y, and z. I need to see my function to do that. So I'll rewrite my function down here. F, x, y, z, we have x cubed minus x, y squared minus z. And for each of those partials, we're going to evaluate them at that point 1, 1, 0. So my partial with respect to x is 3x squared minus y squared. My partial with respect to y is, we've got negative 2y for the derivative of y, so negative 2xy since x is constant. Partial with respect to z is just going to be negative 1. I need to take all of these and evaluate them at that point, 1, 1, 0. So that gives me the partial of f with respect to x at that point. I have 3 times 1 squared minus 1 squared, which is 2. Partial with respect to y at that point is going to be negative 2 times 1, or negative 2. And the partial with respect to z at my given point is negative 1. So my partials evaluated at the point 2, negative 2, and negative 1. So that means my gradient, remember, the gradient is those partials evaluated at the point. The gradient at 1, 1, 0 is going to be 2i minus 2j, and then minus 1k. Therefore, the directional derivative is this gradient dotted with my unit vector. So I'm going to rewrite my unit vector down here. U was 2/7 I minus 3/7 j plus 6/7 k. So the gradient f dotted with u is 2 times 2/7 minus 2 times negative 3/7 minus 1 times 6/7, and that gives me 4/7 plus 6/7, that's 10/7 minus 6/7 goes back to being 4/7. So 4/7 represents the value of the derivative in the direction of that provided vector v. All right, so we found our directional derivative for the function in the direction of v at the point 1, 1, 0. So we have another part of the question. We just completed part A. Part B says, in what direction does the function change most rapidly at the point? And then what are the rates of change in these directions? And so really there could be more than one direction. There should be an S there. I'm too far in to go back and delete. So in what directions does the function change most rapidly at the point? So there can be more than one. And then what are the rates of change in these two directions? And so that was kind of leading because I said the two directions. But in order to do this problem, I'm actually going to go to the next page. We need the gradient of f at that point, 1, 1, 0. And we already calculated that. That was 2i minus 2j minus k. So we know that it increases most rapidly in the direction of the gradient, and then it decreases most rapidly in the direction of negative f. So the magnitude of the gradient of f is 2 squared plus negative 2 squared plus negative 1 squared, which gives me the square root of 9 or 3. And then negative the gradient of f. That would just be that 3 negated. So to reiterate, this gradient here, this gradient has a magnitude of 3. So that is the rate of change. That's our maximum rate of change. That's the rate at which this function is going up or increasing the fastest. And then exactly opposite that, in the negative direction, that negative gradient would be negative 2i plus 2j plus k, going exactly opposite. We would have that magnitude of our, gradient being negative 3. All right, so it works the same way with 3 variables as it does with 2 variables, and we could extend these to higher quantities of variables, but we're not going to do that. So as always, email me if you have any questions. Good luck out in the real world.